Okay, let's quickly talk about electric field lines, and we'll go ahead and cover dipoles in this video as well. That'll be pretty short. So remember, electric charges create electric field vectors at every point in space. So if I have a charge here at the origin, that's going to create vectors everywhere in space. But that gets tedious drawing out all these little tiny vectors. So what we'll tend to do is connect vectors together. If, say, this guy is pointing at that one, that's pointing at that one, and so forth, we'll just connect those together into what we call an electric field line. It's just a bunch of little vectors added together. So here are pictures of electric field lines. These are really just a bunch of vectors. And really, this should fill up the entire screen here. We can't draw them all because then it's impossible to see anything. So we just draw a representative sample. So electric field lines emanate out from positive charge and back in toward negative charges. So if I had this thing called a dipole here, which is a positive and a negative separated by some distance d, this is what the electric field would look like around that dipole. Electric field lines would flow out from the positive into the negative. A lot of electrostatics was developed in the language of hydrostatics. That's the way they really thought of electrical forces and fields. They really believed something was flowing. So that we tend to call positive charges sources of an electric field and negative charges sinks, because that's what we would say in fluid dynamics. So we could think of the electric field here as like your positive charge is your faucet. You've got the faucet turned on and water is flowing into the universe. We call that a source of the field. And then the negative charge is like the drain of your sink, and water or electric field is flowing back out and disappearing. And that's the way the people who developed all this, thought of the electric field. They literally thought some fluid was flowing. We know now that it's not, but it is a great analogy. And then when we have an electric field that's already established, if we place a charged particle in an electric field, positive charges will move in the direction of flow, and negative charges will move against the direction of flow. So literally think of this like water flowing. Think of this like currents. So I have these currents flowing here. Think like water currents, not electric currents. That's not what I mean. This is just an analogy. Think of this like water flowing, and I put a little boat right here. It's going to flow along this line. Same thing would happen if I put a positive charge right there. It would flow. A negative charge goes against the electric field, so a negative charge would flow backwards. Okay, now we're not going to get into drawing really complicated electric field diagrams, so this is not something we really need to worry about. But the way we handle magnitude when we're drawing electric field lines, since we can't make vectors bigger because we're not drawing the vectors, we use density. The denser the electric field lines are through some cross-sectional surface, the stronger the electric field is. So this has a stronger electric field, S prime does, than S does, because the lines are closer together. Closer together means stronger, further apart means weaker. And we'll use that in a couple of pictures. Okay, so this covers a lot of the stuff I just said. Electric field lines always come out of positive and then either go to infinity or hit a negative and disappear, or they start from infinity and go to a negative charge and disappear. And this is important. Electric field lines will never cross over each other. That's just not physically possible. Okay, so here are the electric field lines we might see from a few different charge distributions. Here's that dipole. we talked about a moment ago. Here's what we would get if we had two positive charges. Here is a closer up picture of a dipole. Okay, so let's talk about dipoles. So again, a dipole looks like this. It's a positive and a negative charge kind of glued together, held close by. Water forms a dipole. You've all seen the Mickey Mouse looking picture you get from a water molecule. That will form a dipole where one side of the molecule is more positive and the other side is more negative. If you place a dipole, a positive and a negative charge, in an existing electric field, and you make sure that they don't separate, somehow you've got them restrained so they're always going to stay the same distance d apart. Like in a water molecule, we're not going to break our water molecule apart, but if we put it in a slight electric field, the positive side wants to flow in the direction of the field, the negative side wants to flow against the field. What will happen is this whole thing will rotate. We get a torque on a dipole. Okay, so that torque is given by Q being the amount of charge that we have at the positive charge, D being the distance between them. This D vector is the vector that points from negative to positive, and that's going to cross E. That's a cross product. That would be right-hand rule. We get a torque that makes this dipole rotate. This is the way your microwave works. Water has a dipole moment. When we put it in an oscillating electric field, we make those water molecules spin and then spin back, spin and then spin back. Well, that rotational energy is converted into kinetic energy. And if you have a whole lot of individual kinetic energies, we call that temperature. So we increase the temperature, we heat it up. That becomes thermal energy. Okay, so we have this thing called the dipole moment, which is Q times that D vector. So this is a vector that points from the negative to the positive charge in the dipole. And it has magnitude Q times the distance between them, where Q is the positive charge. Here's that torque. We're not going to do much with it other than know that it rotates. Neutral atoms can be turned into dipoles. We can induce a dipole moment by putting a neutral atom or molecule in a strong electric field, and that will cause some charge separation, make the electrons hang out more on one side and the nucleus in the other. Well, I guess it would be the other way. The electrons would hang out back here. And so from negative to positive, we get our dipole moment. Here's what the electric field of a dipole looks like. This dipole, no matter what orientation it was in to begin with, will rotate to line up with the electric field here. And then far away from a dipole, the electric field caused by a dipole drops off like 1 over the distance cubed instead of 1 over distance squared. And that's about all we're going to do with dipoles.